Hi guys, it's Sydney. Today we're doing Big Idea 5, Thermochemistry. Who's ready to learn?
Thermochem. So for thermochem, the first part that we're going to look at is actually bond strength and bond energy. And so when we're looking at bond strength, that's just literally the strength of the bond between two atoms. And so it's determined by first how close they are together. So if the nuclei are very close together, that's going to be a really strong bond. But then we can also look at bond order. And so bond order is really based on the multiple bonds. So if we have a double or a triple bond, that pulls the atoms closer together. So like the triple bond is the strongest bond, then the double bond, and then the single bond is actually the weakest of the three. So bond energy. When we talk about bond energy, that's the energy required to break a bond. It is always endothermic. So breaking bonds always requires energy. And so whenever you are breaking any bond, it's always going to be endothermic. And so there's three factors that affect it. And the first is size. So if you're looking at like HCl versus HBr, HCl, we have HCl, the chlorine and the hydrogen are closer together than the H and the Br. And so then polarity, we have HCl versus like the CH bond, and then bond order looks at having a double bond versus a triple bond. And then this graph just shows the most stable, the most stable energy for a bond. So the most stable state, so if this is like H2, this shows the radius between the two, and the most stable state is down here at the bottom. That's where your attractive forces and your repulsive forces balance out, and that's where you have the most stable state, which is the lowest potential energy. So a practice question, this is from 2005, so this is from a while ago, but it says the bond energy of the carbon to sulfur bond in CS2 is 577 kilojoules per mole. Is the bond energy of carbon to selenium, so again, always look at the periodic table and figure out what's the biggest difference. So the biggest difference here is the selenium and sulfur. So selenium is in a lower row, but it's in the same group. So is carbon-selenium bond expected to be greater than, less than, or equal to this value, and justify your answer. So if you take a look at sulfur versus selenium, selenium is in a lower or I should say it's below sulfur, and so it's in a higher energy level. So that means that your selenium nuclei and your carbon nuclei are going to be further apart. And so because selenium is a larger atom, it is easier to break that bond. So selenium's atom is bigger than sulfur's, which means selenium's nucleus and carbon's nucleus are further apart, so they're not as attracted to each other. And so that is going to make the bond energy less. That means it's easier to break the carbon-selenium bond than it is the carbon-sulfur bond. Maxwell-Boltzmann distribution we look at when we talk about gases, but this goes along with thermochemistry because it's looking at kinetic energy. And so temperature is a measure of average kinetic energy. Don't forget that. Temperature is average kinetic energy. If something is at the same temperature, it has the same average kinetic energy. And so this distribution just shows the distribution of atoms and their energy. And so like over here, all of these atoms have a much higher kinetic energy than these atoms down here. And so then increasing the temperature will also increase the average kinetic energy of any molecule. But the biggest thing when you're looking at kinetic energy is that kinetic energy and temperature are essentially one and the same. So this question says, consider the three gases in the tank at 327 degrees Celsius. So you have methanol, carbon monoxide, and hydrogen gas. How do the average kinetic energies of the molecules of the gases compare, and explain? So how would we answer part 1? How do the average kinetic energies compare? They're equal. Right, they're all at the same temperature, which means they all have the same average kinetic energy. But then part 2 says which gas has the highest average speed. So now we're actually looking at how fast they're moving, and so since they all have the same kinetic energy, when we're looking at speed, we have to look at mass. And so when you think about speed, you want to think about which one is the smallest. That's the one that's going to move the fastest. And so, in this case, H2 will have the highest speed. These would more likely be multiple choice questions now than free response. 2011 was before they redid the AP test, and so they would more than likely, these would be two, I could very likely see both of these questions as multiple choice questions on the AP test. So some vocabulary for thermodynamics and thermochemistry. So the universe is everything. System, what we want to look at, surroundings, everything else, and then endothermic and exothermic. So endo goes into the system, exo it exits the system. So always think about when you take the temperature, typically you take the temperature of the surroundings. So if you have a beaker and you feel a beaker, but the reaction is actually inside of it, you're feeling the surroundings. Same with like when a fire is burning, you are part of the surroundings, so you feel hot. So you have to kind of think about what that means about the system, which would be like the fire, or which would be the reaction in the beaker. And so here's one. It says, student performs an experiment to determine the enthalpy of solution. They place water into a coffee cup and then add solid urea into the water and measures the temperature. Here is the temperature. So you start at 25 and then your temperature drops over time. And so when you are looking at a solution being formed, your solid is the system, everything else is the surroundings. So when you are taking the temperature of this, you are actually taking the temperature of the surroundings. And so if the temperature of your surroundings is decreasing, what does that mean about your system? Yeah, so your system is actually taking in energy, right? Your system is absorbing energy, which is why your surroundings are getting colder. So it's actually an endothermic reaction, because the decrease in temperature of the surroundings is telling us that the urea is actually absorbing energy in. Heat transfer. So heat is always transferred, or I should say energy is always transferred. Just like mass, energy cannot be lost. And so kinetic energy is actually transferred between the particles if the temperatures are different. Heat always goes from higher energy, so the higher temperature, to lower energy, which is the lower temperature, by collisions. And then when the temperatures are equal, they are in thermal equilibrium. Thermal just means heat. So that's why like thermochemistry is the chemistry of heat. Not all particles absorb or release the same amount of heat. That's heat capacity. Right? Not all particles have the same heat capacity. But heat capacity is the amount of energy that it takes to heat 1 gram of something by 1 degree Celsius or 1 degree Kelvin. And that's when we use MC delta T. And so whenever you're thinking about specific heat, water tends to have one of the highest specific heats. It takes a lot of energy to heat up, and it takes a while to cool down. So another free response question from 2010. These are a little bit older free response questions because we have not seen many free response questions on calorimetry until last year. And we'll look at the one from last year. So this is one that we did yesterday. Assume that the specific heat capacity of the calorimeter is negligible and that the specific heat of the solution is 4.2. Calculate the heat of dissolution of the urea in joules. So when you are calculating heat, heat is Q, right? Heat is Q, Q equals MC delta T. So if we assume that no heat is lost from the calorimeter, that means we don't have to worry about C-cal. But remember that Q lost equals Q gained. So in this case, they just added them together, but we could do it like this. Here's the heat of my solution. It's equal to the negative heat that my solid solution, negative Q of reaction. So when we look at this, Q solution, MC delta T, if you are looking for the heat of the entire solution, you have to make sure that your mass is the mass of the entire solution. And so you have to actually add your solute plus your solvent to get your mass of your solution. Your C is what they give you, your delta T. Now in the case of this delta T, they gave you that graph. That's how you find your delta T. So that graph, you had the initial temperature and then you had your final temperature. That's how we can get this delta T. And so Q of the solution is MC delta T, and so it is 1.3 times 10 to the third joules, or you can divide that by 1,000 to get your kilojoules. And notice in this case, you had 1 point just for the right setup. So if we're using Q equals MC delta T, you got a point. And then the other point is earned for the correct numerical result. So in this case, they don't care about the sign, because it doesn't say for the correct sign. Sometimes they care, sometimes they don't. You don't know until they come out with the scoring guidelines. Conservation of energy, like I said, energy is neither created nor destroyed, but it can be transferred as work or as heat. We didn't do as much with work, but that delta E stands for the total energy is always equal to Q plus work. Work is negative P times delta V. This is all based on gases, but we always assume that it's constant pressure, and so work doesn't even matter for us. So we really don't even worry about this, because normally when we calculate heat, we calculate it at constant pressure, so this entire thing would be 0, and so it doesn't matter for us. Again, with conservation of energy, other ways that we can have work is by expanding or compressing a gas. And then if your volume increases, work is done by the gas because your gas is pushing up. If volume decreases, you're pushing the gas down, and so you're doing work on the gas. And so that's just looking at more of the physics side of looking at work. So conservation of energy when mixing. So this kind of goes along with looking at solutions. And so energy is always transferred between systems that are in contact with one another. They have to be in contact. You can't transfer energy if something isn't in contact. Energy lost by one system is always gained by the other, and so that's why negative Q lost equals Q gained. You know which one will be negative and which one will be positive based on temperature. So like with that last free response question, we answered the first part and we said that the heat of the urea was going to be endothermic because it absorbed energy, so we knew it was going to be positive. And then another way that you can represent this, negative Q lost equals plus Q gained, is just adding them together. All right, so like the heat of the solid plus the heat of the water has to equal 0 because energy is always conserved. So then calorimetry, we did quite a few calorimetry problems, but this is just how we determine heat. You can use it to solve for heat capacity of the calorimeter, which you guys did. You can use it to find the specific heat of a substance, which you guys did. And then you can also use it to actually find the heat of fusion of water, or the heat of vaporization of water, or the overall heat of reaction, which is when we were just dissolving solids in water. So just some of the math that it shows you here as well, because we always have to have the law of conservation of energy. We always have a positive Q has to equal a negative Q. And then you can look at all of this right here. Q equals C delta T for the calorimeter, or MC delta T for a solution. The reason we don't use M in the calorimeter is because the heat capacity of the calorimeter is already taken into account. And so really this, you can see it down here, right? Heat of reaction equals negative Q of the calorimeter, and the Q of the calorimeter is negative C delta T. If you know the heat capacity of the calorimeter, they probably will not have you solve for it. They will give you the heat capacities, and then you are normally going to have to find heat, because then more than likely they're going to ask you to find delta H.
Is that used for bomb calorimetry, or is that also calorimetry?
So it would be both. If it tells you that the calorimeter absorbs energy, you have to take this C delta T into account. Because if the calorimeter absorbs energy, then you're going to have Q of the calorimeter plus Q of the solution equaling 0. Because whatever the solution loses, it will go into the calorimeter. But if the calorimeter does not absorb any heat and we can ignore it, then we don't need this part at all. So then if we don't have to worry about the calorimeter, then we can just use MC delta T. And then notice down here, when calculating delta H, we have to take into account the mass of reactant that caused our Q. So that's why your delta H is always joules or kilojoules per mole or per gram of however many reactants, whatever mass of reactant that we used. This was actually from last year's test. This was a free response question, and it told you that to measure the delta H for lithium chloride, Student adds 100 grams of water at 15 degrees Celsius and then adds 10 grams of lithium chloride and stirs. After the lithium chloride dissolves completely, the maximum temperature reached by the solution is 35.6 degrees Celsius. So when you record the temperature of a solution, you are recording the surroundings. And so if we went from 15 to 35.6 of the surroundings, what did your system do? If your temperature of the surroundings increased about 25 degrees Celsius, where did that energy come from? The system. And so if your surroundings temperature increased, that means your surroundings got more energy, and that's because your system released it, which means this is an exothermic reaction. And so this says calculate the magnitude of the heat. Heat is Q. It will tell you, if it wants you to calculate delta H, it will say enthalpy. Heat is Q. So calculate the magnitude of the heat absorbed by the solution. By the solution, that's a key word. During the process, assuming the specific heat capacity of the solution is 4.18 and include units. So because you want the heat of the solution, you're going to do MC delta T. Your mass must be the entire solution. It must be solute plus solvent. And then you multiply by specific heat, you multiply by your delta T, and then you get your Q. Again, all they want here is correct setup, so MC delta T, and they're just looking for your value with units. So just kilojoules or joules, because everything else is canceled. So then your systems can really undergo three main processes. It can heat or cool, it can undergo a phase change, or you can have a chemical reaction. And so looking at these heating and cooling curves, if you start with something that's a solid and you heat it up all the way to a gas, draw your heating and cooling curve to help you figure out how you have to calculate Q. Because in this part, what the heck is that? Right, in this part, and this part, what is all of your heat that's being added being used to do? In this one, heat it up, right? Phase changes are where they plateau. So in these inclines, all of the heat that you're putting in is being used to heat up the substance. And so that's Q equals MC delta T. Whenever you have these inclines, that's Q equals MC delta T. These phase changes, these plateaus, the temperature isn't changing, so we don't have a delta T. And so these plateaus are where we have to use Q equals M times delta H. And so if we need to figure out the amount of heat it takes to go from a solid up here to a gas, we're going to have to do MC delta T, M delta H, MC delta T, M delta H, MC delta T. And so a heating curve is going to help if you're starting at a specific temperature and you're not sure where you're finishing. Cooling curve is just the other way, right? You just decrease. But anytime you plateau, all of your heat is being used or being lost to undergo phase changes. So here's an example. A student is using a calorimeter made from a cup and a thermometer. Cup was weighed, filled with 100 milliliters of water. After the water reached equilibrium, it was 25, and then you put a metal in. After the solid was placed in the water, the temperature of the water reached a maximum temperature of 40 degrees Celsius. During the experiment, the student failed to put a top on the cup. How would this have affected the calculated value for the specific heat capacity of the unknown? And so what you really need to do is you kind of need to break this question down into what all is happening. So you put in a really, really hot solid into relatively cold water. It's room temperature water, but compared to the 100, it's pretty cold. So if the final temperature was 40 degrees, what happened to the solid? Released heat. Right, it released energy because it went from 100 down to 40. Where did that heat that was released go? Into the water. Right, so all of the heat that was released went into the water. Well, if there was no top on the lid, where would some of the heat have gone? Right, out the cup, somewhere out the cup. And so all of the heat that we should have collected, we did not. So we did not calculate a high enough value of Q. And so since we did not calculate a high enough value of Q, that means that our calculated value of specific heat would also be too small because heat was lost to the surroundings. And so if we would have put a top on the cup, that would have made sure that our Q was as large as it would have had to be. So then that, because specific heat, the top value of specific heat is your joules. Okay, so then this next learning objective looks at the relationship between enthalpy and then breaking and forming bonds. And so when you are looking at breaking and forming bonds, just keep in mind that breaking bonds is always endothermic. Forming bonds is always exothermic, because when you form bonds, you bring two, typically, especially if it's ionic, you bring two oppositely charged ions together. And then if you want to find delta H of the reaction, we do bonds broken minus bonds formed. So bonds broken, and then because bonds forming are negative, this actually we can make as a negative. I simplified it for you guys. So to find the heat of reaction, it is bonds broken minus bonds formed. Because whenever you break bonds, it's always positive, and whenever you form bonds, it's always negative. So if you actually subtract right here, that takes all those negatives into account. When you want to look at bond energies, always draw the Lewis structure. So typically, if it's a free response question, they're going to have you draw the Lewis structure first. That will be part of the question. And then the next part will say calculate the heat of reaction, and they'll give you the bond energies. Don't forget to count how many bonds you're breaking and how many bonds you're forming. And then if you are given standard enthalpies of formation, which is your delta HF, always products minus reactants to calculate delta H there. When you're looking at a reaction being exothermic, that means that you have released energy, which means you are probably forming stronger bonds. So if a reaction is exothermic, you're probably forming stronger bonds and you broke weaker bonds. If it's endothermic, that means that you had to absorb energy, and that means that you probably broke stronger bonds and you formed weaker bonds. So always kind of think about if it takes energy to break bonds and you release energy to form bonds, if a reaction was overall exothermic, that means that you formed stronger bonds. Okay. So this one is from 2003. That's a long time ago. So it says 2 nitrogen atoms combine to form a nitrogen molecule as represented by the following. Use the table of average bond energies below to determine the enthalpy change for the reaction. So we need to figure out delta H of reaction. So here's our equation. Here are bond energies. If you're given bond energies, that means you're doing broken minus formed. So we have to figure out what bonds we broke and what bonds we formed. Well, which bonds did we break? Or did we break? We didn't break any bonds, right? So like that's 0, right? We didn't break any bonds. But which bond did we form? Which one of these 3 bonds? And so now what you have to do is you have to figure out what's the Lewis structure for N2. It's a triple bond. And so when you solve this, because you're not breaking any bonds, that's a 0, minus the bonds that you're forming, which is 950, your delta H of reaction is negative 950 kilojoules. Right? And so it's exothermic because all we're doing is forming bonds here. Right? We're not breaking any. That's why we did 0 minus the 950. Okay, so then looking at some electrostatic forces. So this is kind of going back to intermolecular forces as well. And so we have intermolecular forces between molecules as well as between atoms or ions. And breaking these IMFs requires energy. That's why this is tied into thermochem, because when you break intermolecular forces, you have to use energy. So the stronger the intermolecular forces, the more energy it takes to break it. And so the more energy it takes, that means the higher the boiling point and the lower the vapor pressure. So that's just kind of going back to some properties of liquids. So then here are the IMFs from weakest to strongest. So you have dispersion, which are London forces. Remember, everything has dispersion forces. And so this is also the one that's caused by distorting the electron cloud. And so this is the one that goes along with polarizability. So the larger the electron cloud, the more surface area and the more polarizable the electrons, which means your dispersion forces are stronger. But dispersion forces are still the weaker intermolecular force, so it has the lower boiling point and the higher vapor pressure. Then you have dipole-induced dipole, which is when you have a polar molecule coming near a nonpolar molecule. Dipole-dipole is between two polar molecules. Hydrogen bonding, which is only HNOF, right? H, NOF. And then that's the strongest intermolecular force. We also have ionic bonds. And we have ion dipole, but those only exist when you have ions. So hydrogen bonding is going to be the strongest IMF on here, which means it has the highest boiling point and then the lowest vapor pressure. And so here's a practice for response. So you have dimethyl ether. Now notice these are organic molecules, but you don't have to know anything about organic molecules. You just have to be able to look at this and say, okay, like what's similar, what's different. And so here's dimethyl ether and then ethanol. The normal boiling point of dimethyl ether is 250 Kelvin. Remember, normal boiling point is at 1 atm. That's what normal means. So this is 250, where ethanol is 351. Account for the difference in boiling points. You must discuss both of the substances in your answer. So make sure, if you are comparing two things, make sure that you talk about both of those substances. So what does ethanol have that dimethyl ether does not have? Hydrogen bonds, right? So the intermolecular forces in dimethyl ether are dispersion forces and then pretty weak dipole-dipole, because this oxygen here is technically makes it polar, but it's pretty weak. But then looking at ethanol, you can have London forces, dipole-dipole, and hydrogen bonding. And so since hydrogen bonds are a strong intermolecular force, they take more energy to overcome, and so you have a higher boiling point. Now, here's something that helps. This picture up here, I thought this was pretty clever. Interstates, right, like highways, interstate highways, go between states. Just like intermolecular forces exist between molecules. Intramolecular is inside a molecule. That's covalent bonds or ionic bonds. But intermolecular forces are between molecules. Okay, so then physical change, chemical change, right? Different phase changes. The biggest thing with physical change is it involves intermolecular forces being broken. Boiling, you break IMFs. Chemical change, you're breaking covalent bonds or ionic bonds. So intermolecular forces, which are the ones between molecules, are much weaker than intra, which is like ionic bonds and covalent bonds. And so then this graph or this chart actually shows the strength of bonds, so you can kind of see the difference between all of the strengths. So strong IMFs mean you have high boiling point, high melting point, high viscosity, pretty high surface tension, and low vapor pressure. If you are asked to rank molecules in order of melting point, boiling point, and so on, make sure that you are ranking them by intermolecular forces. So look for molecules that can hydrogen bond, and then look for molecules with dipoles, which are polar, and then the larger molecules will have stronger London forces because they have more electrons. So if you're comparing just molecules with London forces, look at the number of electrons. Okay, so then here is another one for 2013. So compounds 1 and 2 have the same empirical formula, but they have different physical properties. Skeletal structure of one of the two compounds is shown below in box X. Complete the Lewis structure of the molecule in box X. Include any lone pairs of electrons. And then in box Y, Draw the Lewis structure for the other compound, which is a structural isomer of the compound represented. You no longer have to know what isomers mean for the AP test. This was the year before they redid the AP test, and organic was on it. For this one, you would be more likely to be given something like this, and then you have to finish it. So here's actually what everything. Oh, and then this is the second part. So here's the first part with box X. Here is what the first diagram looked like, and then here was the second one that you would have to draw. And so this is like the last one that we looked at. This hydrogen bonds, this does not. And so then you just have to tie that into all the properties. Hydrogen bonding is going to have stronger or higher boiling point, higher melting point, lower vapor pressure, where the one that's just polar and for the most part dispersion forces is going to have weaker properties. So here's one. They made this a learning objective, and it hasn't been asked yet, which means it probably will be this year. So this learning objective ties in intermolecular forces within like biological concepts. More than likely, I could see them asking a question about DNA, because DNA hydrogen bonds. That's how DNA gets that helix shape. But when you have intermolecular forces, again, they're easier to break. And so this shows a protein, and more than likely you would be given an example. So like this would be a multiple choice question, and they would show like 3 pictures, and they would ask which one is hydrogen bonded. And so that ties in DNA. And there's a multiple choice question that we'll probably look at this week when we practice multiple choice, that's going to show like here we have a hydrogen bond between an O and an H, or an N and an H. That's more than likely what the question's going to ask in terms of biological concepts. All right, so then entropy, embrace the chaos. So entropy changes that result in a positive delta S. So remember, positive delta S, replace S with disorder. So a positive disorder means you have lots of it. So when you increase moles, increase temperature, increase volume. And the reason it's when you increase volume is because they have more space to be chaotic. Solid to liquid to gas, and then forming more complicated molecules. And so particle diagrams down here show the solid, and then the liquid, and then the gas. The more disorder, right, the more chaos, the more disorder, the higher the delta S. And so here's another question. It says, here's the combustion of carbon monoxide. Determine the value of delta S of the reaction for the combustion of CO at 298 using this information. And so they give you the entropies of formation of each of these, and they ask you to find the overall delta S of reaction. And so what's like the equation that we can use for really all 3 variables? Yeah, products minus reactants. And so we can take our product, which is our CO2, and then subtract your reactants, taking into account the coefficients. And so notice, like here, 1 point is earned for making sure that you take into account coefficients. So if they see that you did 1/2 times 205.1, that's 1 point right there. And then the other point comes for the answer with the correct sign. And then also make sure you include units. And a lot of times if you're given tables like this, they give you your units. So then predicting how reactions will go, you have this table that we've looked at already. Delta H equals, or delta G equals delta H minus T delta S. Nature likes, this blue arrow is because this is what nature prefers. A negative delta S, a negative delta H, a positive delta S, and that makes your delta G negative at all temperatures. Remember that thermodynamic favorability is the same thing as spontaneity now. And then entropy, this big caution sign, right? Entropy is typically given in joules per Kelvin, and so make sure if you're actually calculating for delta H that you check your units and that you convert. If delta G is negative, it's spontaneous or thermodynamically favorable, and that means the reaction will proceed on its own. So how can you calculate delta G? So there are 3 different ways, and all 3 ways are shown here. Actually, there's 4 different ways. 3 of them are shown here, And you have this little triangle up here which shows the fourth equation right here. And this little table right here actually is pretty useful because it compares delta G to E naught of the cell to K. And so if your delta G is negative, that means something is spontaneous. That means that your cell potential has to be positive and that your K is greater than 1. If you have a non-spontaneous reaction, then your G is positive, your E is negative, and your K is really small. Remember, less than 1 for K just means it's a really small number because K cannot be negative. When you're at equilibrium, delta G and E are both 0, and then K is equal to 1. Other ways that you can find delta G is doing products minus reactants, or H minus T delta S, or negative NF E naught. And finally, you can do delta G equals negative RT ln K. All 4 of those are on your equation sheet. You just have to be able to use them. And again, biggest thing with looking at thermodynamic favorability is you should be able to look at delta G or E. So delta G, if it's negative, it's spontaneous. If E is positive, it's going to be spontaneous. So coupling a reaction, this is when you really couple 2 reactions together, one that's very, very exothermic in order to get an endothermic reaction to proceed as well. And so when you have a very favorable reaction, like the top of that little train up there, and you kind of connect another typically unfavorable reaction with it, that's called coupling, right? Couple is 2. So that would then allow this unfavorable reaction to then become favorable because this endothermic reaction is kind of piggybacking off of the excess energy from this exothermic reaction. And a common example is biological, and I'm not even going to try to pronounce these enzymes because I don't teach biology, but this first reaction, delta G is 0, so it's at equilibrium. But the second reaction, you have a negative delta G, and so when you couple these reactions together, this favorable reaction, this spontaneous reaction, will actually help this other reaction take place on its own. Just talking about, oh yeah, kind of like Robin Hood, right? Robin Hood stole from the rich and gave to the poor. That's kind of what you do with coupling reactions. Right, you steal from the one that is rich in energy, give it to the one that doesn't have as much energy, and then it'll happen. So this is still pretty much the same thing. We just call it Le Chatelier's principle. So if we have one that has a lot of energy, one that doesn't have a lot of energy, and we add energy to the one that normally doesn't have enough, equilibrium will shift. That's Le Chatelier's principle. Okay, I've talked about coupling now. So here's one that kind of comes back to looking at delta H, delta S, and delta G. So for reaction X, will the equilibrium constant increase, decrease, or remain the same if the temperature rises above 298 and justify your answer? So if you're looking at reaction X, you have delta H and delta S. Those are both values at 298. It wants to know what's going to happen to your equilibrium constant. So you could calculate your delta G and then calculate K. Or you could look at it conceptually. I think that for me, I would probably calculate just because I tend to do better with math. And so if we wanted to, we could do delta G equals delta H minus T delta S and then change our temperature to see what happened to delta G. And then based on delta G, we know if it's more or less favorable. And then we could go that way. But in the end, Kp will increase. So our equilibrium constant will become larger. And that's because since this is an endothermic reaction, and we know it's endothermic because delta H is positive, by Le Chatelier's principle, we know that it's going to then go toward the products. And then if it goes toward the products, that means that your K increases. Because remember, temperature changes, or K changes with temperature. So that's why it's asking if K will change. Not Q, but K, because K changes with temperature. Or you could go through and, like I just said, solve for delta G, and then plug it in for K, and you find that K will increase as well. So just being able to go through and go back and forth between all 3 or 4 variables. And so then looking at coupling reactions with standard reduction potential as well. Coupling reactions is also, we can think about it as half reactions. So in order for a battery to work, you had to have half reactions. And so when we couple reactions, we can multiply or we can reverse reactions. This is Hess's law now. So this table right here actually takes all of your K, your delta H, and your cell potential into account when you do Hess's law. So when you multiply, let's say you multiply a reaction by 2. Then if you have delta G, delta H, or delta S, you also multiply that by 2, right? If you're looking at Hess's law. If you multiply a reaction by 2, you don't multiply K, you square K. And if you multiply a reaction by 2, you don't ever multiply cell potential. The only thing that you can do to cell potential is change the sign. And then if you flip the reaction or you reverse it, like we talked about today, you take the inverse, so you take the reciprocal, you would change the sign for delta G or delta H or delta S, and you would change the sign for cell potential. And then if you want to add them all up, you can multiply the values for K, add them up for either E or delta H, delta G, or delta S. And this actually looks at what we looked at today, right? With adding them up, you have to multiply or you add up your delta G's. So is it thermokinetics or equilibrium? So kinetics tells us how fast a reaction goes. Equilibrium tells us how far a reaction goes. So do we make reactants? Do we make products? Do we have equal amounts? Thermodynamics tells us whether or not the reaction is favorable. So kinetics is rates. Equilibrium is do we have more reactants or products? Thermodynamics is it spontaneous or not? A reaction that is thermodynamically favorable or spontaneous will probably form more products at equilibrium, but it could be very slow. So just because a reaction is spontaneous does not mean that it's going to be fast. And so then looking at thermodynamically favorable reactions, so aka spontaneous, means a reaction is product favored, so K is greater than 1 and delta G is negative. But as K decreases, as you get closer and closer to equilibrium, delta G becomes more positive, or that's as you get further from equilibrium. So it kind of depends. When K equals 1, you're at equilibrium and delta G is 0. So this kind of goes along. If delta G is positive here, K is really, really small. When delta G is really negative, K is really big. It's very spontaneous. You have lots of products. When delta G is 0, K is 1, you're at equilibrium. Again, what I just said. So kind of a nice summary table for that. Thermodynamically unfavorable means that it's not spontaneous, but the reverse reaction is spontaneous. And so then this is just a free response question for thermochemistry. Let me check, because I think that this is, yeah, so this is just a practice free response question, and so this is from 2006, but what this does is this walks you through different reactions and figuring out if they're spontaneous or not. So like, is reaction X, is this reaction spontaneous under standard conditions? And then justify your answer with a calculation. So what that means is show a calculation. So if you're looking for something to be spontaneous, what should you calculate? Delta G. So calculate delta G, and then based on your delta G, make sure that you actually answer the question. Make sure you actually answer if it's spontaneous or not. And then calculate the value of the equilibrium constant for the reaction. Well, once you know delta G, you have an equation on your equation sheet that lets you calculate K. And then what effect will an increase in temperature have on the equilibrium constant? So this is where you can look at, in this case, this is an endothermic reaction. And so if it's endothermic, which side would you add heat to? The reactants. So if we have heat over here, if we increase temperature, just figure out which way that's going to shift everything and how that will affect your Q. And then explain why the standard entropy change is greater for y than for x. So here we have a bigger entropy. This wants to know why, so look at your disorder. So you're looking at y is standard entropy change greater for y. So we're going from solid and liquid to a gas versus a solid and a gas to a gas. Above what temperature will the value of the equilibrium constant be greater than 1? So again, this is all going back in and calculating. So when A asked us to calculate delta G, and then answer the question about spontaneity, we can use our negative RT, L, and K to calculate.
Patty Krupa, 1010.
Yikes. So you can use delta G equals negative RT, L, and K to calculate your equilibrium constant. And then right here, when you're looking at increase in temperature.
Correction, Patty Gaston, please out 1010. Patty Gaston, 1010.
So since it's endothermic, it increases in temperature, kind of like we talked about. And then here it goes through standard entropy change. Again, you're just explaining. And then what temperature will the value of the equilibrium constant be greater than 1? So when KQ is 1, delta G is 0. So you plug everything in and solve. And then part F is looking at calculating delta H for a different reaction. And so you can go back in if you need to look at that entire question. That was from 2006, though, so that was a little bit older of a question. They are no longer this math-based. You've been able to tell from free response questions. They used to be math, 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 math. Now it's like, here's some math.
All custodians, please report to the gym to set up for a volleyball match. All custodians to the gym at this time. Thank you.
So it's no longer as much math. It's just some math, some conceptual. But it's still good that you can do the math because you never know what math questions they might throw in.